Good morning, mathematicians. Yeah. Whoa, my mouse just froze. That's interesting. Oh, because I left my stylus on the pad. What are we going to talk about today? Yeah. Probably more demodule stuff. Good morning, Edith Smith. Well, where were we with the demodule stuff? So, right, the point was we get out um, we get out this complex, and so this, whatever a perverse sheaf is, this is one. And what do we want to compute? Well, our understanding of perverse sheaves is uh, really about computing cohomology and then taking the restriction of that cohomology to each strata. So let's look at that. So the first thing to look at is the kernel of the map D. Yeah, the first thing to look at is the kernel of the map D. Well, in this case, right, what is D, how is D acting? It's basically just taking derivatives. You remember you were trying to learn. Oh, do I remember you were trying to learn algebraic geometry? Well, now I remember. So you actually got done with chapter 1 of Hartshorn. Nice. Nice. You're also doing all of the exercises. Well, some of the exercises were unsolved problems, I think, at the time of writing. So don't recommend doing all the exercises. Yeah. But you should do many of them, and it's good that you're doing a lot of exercises. You'll be better at algebraic geometry than me soon, doing all those exercises. End of the summer seems ambitious. We've only got a month and a half left, but I say go for it. I mean, I don't know how much time you're spending on it each day. Maybe you've got a lot of time, in which case, yeah. Then you should be making videos starting in the fall on algebraic geometry. So in this case, notice that this sheaf, this is basically just OX, right? Because we've like, if we think about our sections, over some open set, I mean, it's basically generated by, well, the polynomial ring, and then you invert the elements that are in U, and then also basically the span of the differentials, modulo the equivalence relation. But we've taken the left module of this differential, so we've basically killed all the differential terms, and all that's left of the underlying sheaf is really just OX, or OC, I guess we should say. Okay, this isn't quite, I haven't rigorously provided the sheaf morphism, but yeah, at least from a vibes-based approach, these are isomorphic, right? And so, well, if we think about it, then our differential in this case, and so the basically our complex just becomes the exterior derivative because oh yeah, so let me say one more word about that. You meant most of them, yeah. Literally the only thing you're doing this summer. Awesome. Awesome. Well, yeah, like I said, you should be making videos about it in the fall once you've done it all. And our zero differentials are basically just the structure sheaf as well, right? So this first term is basically just the structure sheaf. And then also, I mean, if we tensor over tensor our one forms, we basically just get back our one forms, right? So really, this just can be realized as the map to one forms. But I mean, basically, if you know, oh, you know what? I lied to you guys. There's a step I forgot. There's a very important step I forgot. Um, um, so, okay, we're gonna have to talk about some fancier things. But morally, we can finish this computation. The thing is, in the Riemann-Hilbert correspondence, we need to pass from the algebraic variety to the analytification. So we basically turn this into a manifold. And we then need to analytify all of our sheaves and all of our D modules so that this actually happens over the analytic category. Yeah. So, yeah, that's an important thing. Okay, but I'm going to continue these. I mean, these computations are like formally identical, but that's actually a very big and significant thing that we can do that. Okay. So, okay, well, we can imagine these are analytic, or we don't have to. I mean, either way, basically, if you know Durham cohomology, we see that this basically just works out to the Durham cohomology of the complex numbers, which is just dimension 1 in degree 0 and 0 everywhere else. Another way to say this is, well, what's in the kernel here? I mean, that is just going to be, I should say, locally constant functions, because again, we're computing this over every open set. Right? And so if you assume that U is some connected open set, this will just be constant functions on here. In other words, so locally constant functions, well, what is this? It's just the sheaf of things that are locally constant. So the kernel, which is to say the homology of the Durham of this D module we started with in degree 0 is just going to be the constant sheaf. And then what about the cohomology in degree 1? Well, that's just going to be 0. Well, no, sorry. The kernel, this is the 0 map. So, I mean, it will be 0, but it's not that immediate. So the kernel is everything. The cohomology is going to be this modulo the image of this map. But we're on the complex numbers, right? So we can just basically use the fundamental theorem of calculus. If we had any function sitting here, we could simply take its derivative, and then the differential will send it to here. I mean, times a dx, because we're in the sheaf of one forms. But so that means that all of the other cohomologies of our sequence are 0. And in particular, so this was the Durham sequence shifted by 1, which means the actual Durham sequence, which is what we're interested in, has cohomology in degree. I always get my shifts backwards. -1. Pretty sure it's -1. Yeah. Hello, duck with a monocle. So all we need to do then to complete what I claim is how we understand perverse sheaves is just look at the restriction to both. Look at the restriction, but of course we can just see the restriction of this to both orbits is just the constant sheaf on both orbits, right? Restrict this to non-zero complex numbers. This is the constant sheaf on the non-zero complex numbers. Just watched a bunch of people have a normal life. Well, don't do that. Don't do that. You watched a bunch of people have a normal life? Where? I don't believe you. I don't believe in people that have a normal life. Yeah. So that basically completes the computation. And we could repeat this with each of the other complexes. So, what else is there to say? I guess we could, yeah. Well, I mean, I already, not to say that I can't talk about these things again, but I already, uh, have done some examples where I computed a bunch of stocks of perverse sheaves and then compared them to representations of p-adic groups and verified that the Kasdan-Lustig hypothesis is true. That's in a bunch of older office hours. So I don't know if I really want to go through all of that again. But this kind of completes the connection in some sense to the D-module perspective. Yeah. Well, what to do next? Actually, there is more to talk about here. And that is, I want to compute the characteristic cycles of these D modules. Now, I don't have a good way to justify why you should care about these characteristic cycles without getting into some very fancy territory. Maybe I should start talking about some fancy territory. So let's go back again and talk more about the Langlands program. So there's the local and the global. Right at the local level, we've got automorphic representations, and we've got Galois representations, and we've got this bridge between them. And then at the local level, we know an automorphic representation, whatever that is, breaks up as a tensor product. And so one maybe hopes that we could break this into a bunch of smaller Langlands correspondences for each of these groups over these local fields, where each of these have their own mappings to Galois groups over the local fields. And then if we could understand this, maybe we can synthesize all of this information down here and feed it into the automorphic Galois machinery. In fact, sometimes proofs seem to go in the other direction. One proves local things using things we know about the global case. But anywho, so there is a notion. Okay, what do we know about automorphic representation? So for example, is this surjective? Like, is it true that if you take any irreducible representation of this group down here, call it pi 2, does there exist an automorphic representation such that this shows up in the factor? And the answer is no. Definitely not. And in fact, usually, most of the time, we even have vague statistics. I wonder, actually, maybe people even have precise statistics, but for automorphic representations, I've talked about this before, almost all, meaning all but finitely many, of these things, well, this doesn't really say much about which representations can or can't appear. But in a given automorphic representation, most of the places this shows up in the maximal compact. Or rather, what should I say? This is generated by the k-fixed points where k is the maximal compact. Or I think this is even just GZP in this case. So that's interesting. And but it still doesn't really actually give us any deeper insight, because you could imagine, like, okay, as you run over automorphic representations. You could have every one of these other things being in the k fixed points, but then this thing, which is outside of the almost all, this one finite representation, you could still imagine that somehow as you run through the list, you hit all of the irreducible representations of this group. Well, it turns out you won't. And part of this next idea is there's these things called Arthur packets. And the idea of these Arthur packets is basically that if I, a representation of this local group, shows up in an automorphic representation, then pi belongs to what's called an Arthur packet. So in other words, you have to go read Arthur's work. I actually don't know the precise technical definition, but so Arthur has some definition of these collections. So I should say this is not, here's not what's true. It's not the case that this is the set of all representations that show up in some automorphic representation. Rather, there's a bunch of these different labels. So each of these sets themselves are going to be a finite set. And so this is really a sort of like, I don't know if I call, what's a name for this? Call it like A, A of GQP. So these are like, as this is bad notation because it conflicts with other things. So this is maybe the set of all automorphic, all representations that show up in automorphic things, and it should be a union, not a disjoint union, crucially, of these things called Arthur packets. So what are these labels? And how are these packets determined? Well, you can already tell by my comment, I'm not going to tell you Arthur's original definition, although I should probably go and learn that. And I promise this has something to do with D modules, but I might not say what that is today. But I can talk about what these labels are. So for the local Langlands correspondence, we have our representations of our group, and we want to send those to representations of the Veydelin group. So actually, I don't know, I've seen W prime and WD, and those are refer to two slightly different versions, and I can't remember which one, but pick whichever one. I'm gonna make a particular choice right now. So I don't know if this is consistent notation with other people's notation, but what I mean is take the Vey group and multiply by SL2C, and a Veydelin representation. Okay, we're gonna get this is the real fancy thing here, is going to go into the L group of G. But actually, in many cases, for simplicity, we'll deal with the split case. So what I mean by this is let's say we were thinking about GLN QP, then I mean that we're going to look at homomorphisms from here into GLNC. If we were looking at SO 2n plus 1 QP, we would be looking at homomorphisms into SP 2NC. And then also vice versa. Yeah. And so an Arthur parameter is actually a very simple thing. An Arthur parameter is now just going to be, instead of one SL2 factor, we have a second SL2 factor. So that's pretty simple. And therefore, we see that each Arthur parameter determines in this way a Langlands parameter. It's actually not just naively restricting to the second factor. It's slightly more complicated, but let's not worry about that right now. And yeah, so in particular, however these Arthur packets are defined, it should be the case that their corresponding Langlands parameter, that is a subset of the corresponding Arthur packet. But this could pick up more representations. Okay, maybe I'll just throw these words out before I end another short office hour. But one of the things to sorry, drawing a blank here. One of the so the connection here to D modules is so I've talked about before that we have this. Well, let me say one other thing. So we also get here each Langlands parameter corresponds to, in turn, just by a sort of, again, restriction, corresponds to what's called an infinitesimal parameter. And in previous office hours, I've talked about the definition of this variety as a sort of, as a variety, it's very boring. It's just affine space. But there's a group action on it that makes it interesting, and it's a sort of moduli space of Langlands parameters with infinitesimal parameter lambda. And so in particular, though, the way that this works is we have a group acting on the space that stratifies it into orbits. By the way, the example of the complex numbers is precisely an example of one of these spaces. And so each of these orbits, though, so the point is that 2 points in this variety are in the same orbit if and only if the Langlands parameters that they correspond to are equivalent. And so that means, in particular, that these Arthur parameters, which give you a Langlands parameter, these should correspond to particular orbits, right? So attached to each of these Arthur parameters is an orbit, and so one can ask. So Arthur has some um, definition for these packets that is built to try and capture representation theoretic information. But so we might wonder, um, is there like a geometric characterization of these orbits? Um, Probably not, but also kind of. Well, but what's more interesting is the thing is this Arthur packet is generally larger than the L packet it contains. So maybe a better question is there a geometric characterization of the Arthur packet itself? And so another thing that maybe you remember, maybe not from previous videos, is that if is that the local Langlands correspondence can be promoted to a bijection, where the bijection is between uh, a representation gets sent to a pair, where the first thing in the pair is the orbit um, of its Langlands parameter in the corresponding Vogel variety. Nerdy Quagsire doesn't remember much of anything. Well, you gotta do more homework then. That's how you break through. But I guess the problem is you have to remember to do your homework, and if you don't remember much of anything, that'll be tough. Um, and then you also take a particular choice of local system on that orbit. So here's a connection, right? This is why I spend so much time talking about local systems and D modules and stuff. Great. So yeah. So in other words, we could then so we know that every pair of an orbit and a local system corresponds to unique irreducible representation. So we might introduce a notation, pi CL, for the representation attached to this pair. And we might then try and ask the following: can we characterize? And again, I mean, this is silly because I haven't even told you the definition of Arthur packets. But can we characterize those representations which appear in some given Arthur packet in terms of the geometry of the pair C and L? And it turns out that the answer, there's different perspectives on this, but one way to answer this question is the conjecture. And I'm going to state this very imprecisely, but we'll get into it in future episodes. The conjecture is that this has to do, again, this is not a precise statement, but this has to do with the characteristic cycles, or what's sometimes called the singular support of the D module associated to the pair C and L. So um, this probably made sense to no one but me. Unless in the off chance there's someone tuning in who already knows this stuff. Um, but this is the big idea of where this is going and why I care about it. Okay, should I talk about less complicated things? I feel like I came back to office hours and then I just like slammed my foot on the gas pedal 1,000%. Um, oh, never mind. It's trivial for a Quagsire. You learned this when you were 5. Oh yeah. Oh, interesting. Wow. Okay, then maybe I look forward to your explanation of it then. I would love I'd love I'd love for you to sit down and explain the answer to me. It's okay. I know nerdy Quagsire in real life. I know uh yeah. I know the truth of where they stand. You understand my reasoning? We've never seen this before. Uh yeah. I don't know why you understand the reasoning. Actually, here's something I might start doing in my office hours. I might start going through the book of Bushnell and Art on Langlands for GL2 and skip ahead to the parts that I'm most interested in. I think that's my plan. Yeah. Oh, you're an anonymous online user. Okay. Okay. Sure, nerdy Quagsire. You want to still pretend that we both don't know the truth. That's fine. That's absolutely fine. I know you think I'm stupid, um, as evidenced by these trivial things that you knew when you were 5. But anyways, I'm gonna call it there because I want to go do some work. Want to yeah, go hit the bench, go hit the books, do some tutoring, work on uh, work on some papers, plural. Work on some papers, plural. Is that a good idea? Should I finish the next paper first before starting the next one? Probably. Aren't we all stupid? Yes, they said. Yes, we all are. But even though we're stupid, we should all go and prove things right now. So, yeah, I'll go prove Langlands. You guys go prove whatever you're working on. And we'll meet back here tomorrow. Maybe. I might skip stream tomorrow. We'll see. Depends what time I get up.